So if you look on the table, you will see it says roughly about 3,300 centimetres to the -1. I don't know what exactly the range is on the data table. It's around that number. I really don't care what the number is on it, because that doesn't help us to interpret this table. So this is the information that you get on this. Now, that's not really very much information. You need to know, there's more information you want to know about the expected peak for an OH that makes it very, very easy to spot on here. So the characteristic of the alcoholic absorbance is that it's very broad, and typically it's strong. So the broad represents how wide that peak is going to be, and the strength is how far down it's going to go. So that's the first thing you need to kind of get into your mind, is that we're actually looking at the things that go down. I imagine your first instinct is to look at the bits that go up. So you might be looking at this bit here, this bit here, this bit here, this bit here. Now that's actually not the thing you're looking for. If we cast our minds back to how it works, we're looking for the things that got absorbed by the sample. So we're looking for the gaps in the spectra where light has been absorbed, and so we've got low transmittance. So we're looking at the bits that go down. So here, 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 and here. Those are the things that are interesting to us. Now, I've only drawn on a rough scale, but if we look at around 3,300, we have a very broad peak here. We call them peaks even though they go down. We usually use the term peak in other spectra, and so even though it points down, we still use the word peak. And this is the alcohol OH. Now, the reason I've drawn the bond in there is that bond vibrating that's causing this absorbance of these wavelengths of infrared light. And it has a characteristic U shape. So I always think it looks a bit like a letter U. And so this should really, really stand out. Now, you're not going to write anything about it being broad or U-shaped or strong in exam questions. They're just going to want you to write down the number or the range from the data table. So you don't need to memorize that range. You just need to know roughly 3,300. That should be what's in your mind that you remember, so that you just look at a spectrum and go, right, it's got this U-shape, it's broad, it's around 3,300. So I can be really, really confident that this is an alcohol OH peak. Now, we've got here, so we'll pretty much always see these peaks in a spectrum. It's generally very messy, and this is because we've got lots and lots of peaks overlapping with each other. These are CHs, multiple different CH absorbances. This is because almost every single organic molecule that we're going to come across has a CH bond. So that is almost always there in every single spectra. I don't think I've ever seen a spectra that's come up in an exam paper that doesn't have some peaks here. And a really common mistake is to misassign this to other bonds that overlap this range. So it's typically around 3,000, maybe just slightly below. So I'd say between 2,900 and 3,000 is where you generally get these groupings of peaks here. Now, there are other absorbances or functional groups that are interesting to overlap with that range. And so if you don't know that this sort of bunching up of peaks is going to be the CH, you're going to misassign that to maybe a carboxylic acid OH. So you need to actually be able to recognize this, not just rely on the data table. So you're going to see this grouping of peaks. You're going to see that in all the spectra that we look at in the work that I'm going to set you on Frog. Now, moving down, we've got this sort of mid-absorbance broad thing. That's nothing to be interested on. That's not one of the characteristic peaks we're looking at. And then we get to everything below 1,500. Now, everything below here, this doesn't actually represent individual bonds vibrating. This represents the molecule as a whole sort of flexing. So we've got to think in a more complex manner than just the one bond between two atoms, rather than the bond just vibrating back and forwards. This is a whole molecule sort of flexing around. So they don't correspond to individual bonds within molecules, which makes it basically impossible to interpret. So we can't gain any useful information just using if you're just using a data table to interpret any of this. This is called the fingerprint region. Now, that name, the fingerprint region, that gives a bit of a clue as to what it can be used for usefully. So the absorbances within this region are specific to the exact molecule. Now, there's no real way of predicting this, so I can't predict where peaks are going to be in the fingerprint region for ethanol. I can predict with pretty good accuracy what things I'm going to see up this end of the spectrum, because this OH peak is going to appear in every single alcohol. It's basically going to be identical, whether it's ethanol, methanol, propanol, butanol, but the fingerprint region is going to be drastically different for each of those. So where we can use it is if I've got a reference database of spectra, so I can look to compare the fingerprint region of an unknown molecule that I've collected. So I've maybe got an unknown sample of an alcohol. I've identified it as an alcohol because of the alcoholic OH, but I don't know whether it's methanol, ethanol, propanol, or butanol. If I take the infrared spectra and then compare the fingerprint region to already pre-prepared infrared spectra of each of those alcohols, this region is going to look basically the same in all of them. That's not going to be useful. But the fingerprint region is going to be drastically different between methanol, ethanol, propanol, and butanol. And so I can match up the peaks in the fingerprint region. So what you'll be asked in an exam is maybe what this region is called and how it's used. And the way it's used is you compare it to a database and look for an exact match. And that's the language you want to be using. So compare to a database and look for an exact match. That's that 1 mark statement you're going to write in about what's the use of this region below 1,500. And another 1 mark might be what's the name of this region, so the fingerprint region. So that's all the useful stuff really from this spectrum. I've identified the alcohol OH and I've identified the CHs. This is the only one that's of any use, CHs. Make a note that they're there, just so you don't get them mixed up with anything else. Right. Now, I've got one more prepared here, which this one is carboxylic acid. Now, the carboxylic acid group this has two of the things that we are going to expect to be able to see on a spectrum. So we've got the carbonyl and we've got an OH. Now carbonyls, the CO double bond, they always show up at around 1,700. I think the range on the database is 1680 to 1750, or maybe 1730. Now this generally shows up, it's generally a very strong, it's usually quite narrow. It's sometimes a bit broader for a carboxylic acid, and around 1700. So this peak here, this corresponds to the carbonyl. That's the CO double bond. Now that just on its own, certainly at A level, you couldn't distinguish it between a ketone, an aldehyde, or a carboxylic acid. All of those groups have a carbonyl, and to you at A level, this peak is indistinguishable between those different functional groups. So I know from this, I've got a carbonyl, it's at around 1,700 centimeters to the -1. It's quite a strong absorbance, it goes quite a long way down, and it's generally pretty narrow. Now this is not that narrow. If you took a ketone, for example, it would be very, very thin. So the peak would be at least half the width, probably narrower than that, and it can get really, really low down. So very pointy, it's one of the easiest ones to spot. Now moving over here, my diagram is perhaps not perfect. It doesn't normally look this smooth. As we have CH bonds in there, we have peaks due to the CH bonds coming in at normally around 2,900 to 3,000. So normally overlapping this will be those peaks from the CHs. And what that tends to do to this absorbance here, so this is the OH from the carboxylic acid, is it tends to change the overall shape and it makes it look more V-shaped. So my diagram doesn't show that very clearly, but it will be fairly clear on some of the examples that you see in the work that I'm setting you. It tends to form more of a V shape. And if we look at at where that absorbance is centered around, so with the alcohol OH, it was centered around 3,300, so up around here. This, it should be more like 2,900 to 3,000, so I've maybe drawn it a little bit over to the left. And so if you look carefully, you can quite easily distinguish between a carboxylic acid OH, So this is an acid OH versus an alcoholic OH. It's a common mistake and get them mixed up because you see a very broad peak over to the left of the graph. Students don't check to see if there's a peak where it's centered around, and so they misassign it as an OH group. Sometimes they'll try and throw you off the scent by having a molecule that has the CO double bond and an OH, but it's not a carboxylic acid. So if we took, for example, this molecule here, that would have a spectrum that at first glance would be very similar to a carboxylic acid. It's got the CO double bond, and so we'd expect to see the peak here, and it's got an OH group, so we'd expect to see a broad peak on the left-hand side. But you'd have to look carefully at where this OH peak is centered. So if it's more U-shaped and over at 3,300, then it could be something like this with the OH group that's not part of the carboxylic